most important everyday solutions that we come across of aqueous solutions are acids and bases. So we're going to be working with acids and bases in an upcoming lab. But first, let's define acids. So hydrogen is always the cation, and what happens with acids is that they always will release the hydrogen ion in the aqueous solution. So you have hydrogen ion, and then any anion, any negative charge. It can be a single, a monoatomic anion, like in HCl, or it can be a polyatomic, such as the sulfate in H2SO4. So depending on the charge value of the anion, you're going to have a certain number of hydrogens in order to match the charge value. So that hydrogen is the cation, and it is sometimes called a proton. That's because it's a hydrogen ion minus the electron. And when you take away the electron from the hydrogen ion, all you have left is a proton. Is an aqueous hydrochloric acid solution. So when an acids are always aqueous. They are always dissolved, and acids are soluble. So that's rule 6 of the solubility rules. So you should always have an AQ, physical state, for any acid. The aqueous solution, you can always split apart into the ions. So the ions of HCl are the hydrogen, H+, and the Cl, that's the anion, minus. And they're both aqueous, meaning they are dissolved in the solution. And so this hydrogen ion will attach to the water molecule in the aqueous solution, and this forms this H3O+. So you actually have 3 hydrogens and then the positive charge, and this is called the hydronium ion. So this is written interchangeably, that this is written as H3O+, and it's written as H+, because you're always going to have water around, and this can always form. So the chloride ion is still exactly the same. That doesn't attach to anything. Okay, and so this is the hydronium ion. It's really just the water molecule with an extra hydrogen ion. When you have HCl, hydrochloric acid, is that it is an aqueous solution. Acids are always going to be soluble. And then this breaks apart into H+, that is attached to an H2O. So that's an H+ attached to an H2O, and that's written as H3O+, or just H+, and then you also have the chloride ion. Strong acids are completely dissociated. They completely break apart, and they are ionized. So they are all ions, and it's all a forward reaction arrow. Okay, so this is because they're completely dissociated, and it's not necessarily a reaction as so much as it is that you don't have this HCl, you actually have H+ ions that are dissolved and aqueous, and you have Cl- that are dissolved in aqueous. Or instead of, this is nitric acid, HNO3. Instead of HNO3, you don't actually have HNO3, you have H+ that are aqueous ions, and NO3- that are aqueous ions. And then this is sulfuric acid, H2SO4. This, you don't actually have this compound, but instead this is broken apart into the hydrogen ion, and there's going to be 2 of them because of the subscript, and the sulfate ion, SO4 2-, and that's the 2, becomes the coefficient and also the charge value on this sulfate ion. Weak acids are a little different. Weak acids still have the hydrogen cation, but they are not completely dissociated. So you have a reverse reaction. So it's a 2-way arrow. It's a bidirectional or 2-way arrow that is both forward and reverse. Okay, so that's because they're not completely dissociated into the ions. The ions turn around and they reform the compound. And so they reform the ionic compound, which is the acid. So there's a reverse reaction, that's the double-headed arrow, or 2 opposing arrows. So you can either have the double-headed arrow like this, or 2 opposing arrows. Okay, so acetic acid in vinegar, this is a weak acid, and this weak acid is indicated by this double-headed arrow, which is that this breaks apart into the ions H plus and the acetate ion. Okay, so that's the acetate ion from the polyatomic ions list. And this doesn't break apart into all different atoms. Okay, so this remains together. And the difference is that there's this double-headed arrow. So it means that you have some ions in the solution, and you also have this compound in solution. You also have the ionic compound, so you have the ions and you also have this. So you don't have all ions, which is the case for a strong acid. So there are acids and bases, and both are aqueous solutions. So this is still an aqueous solution, but this has this hydroxide ion is always a part of the base in some way. So bases, you can recognize they have a bitter taste and they're slippery, and soaps are usually bases. So slippery, and if you ever taste it, it's bitter. But what all bases have in common is they either produce hydroxide ion in the aqueous solution, or the bases already have the hydroxide ion as part of the ionic compound. So this is a common base that you might have around the house. It's called lye, and it is sodium hydroxide. So hydroxide is already part of the name. Okay. So strong bases are completely dissociated. So they are completely ionized, and so you have all ions, and this is a forward reaction arrow. When you have these strong bases, NaOH, KOH, and CaOH2, those all have the hydroxide ion. The calcium hydroxide is an example of a strong base, and it's completely dissociated into ions. And so this is the calcium hydroxide chemical formula. And so you don't have this. What you actually have are these ions, which are the calcium ion. And this 2, you'll notice, goes 2 places. It becomes the charge value, and you have calcium 2 plus. And it also becomes the coefficient, because when this breaks apart, you're going to end up with 2 hydroxides. So you have these ions, but you don't have any of this ionic compound for strong bases. Weak bases, where you have a reverse reaction, just like the weak acids. Okay, so you either have the double-headed arrow, or you have a forward and a reverse arrow. So ammonia, NH3, is an example of a weak base. This does not have a hydroxide group, but this does produce hydroxide in aqueous solution. Okay, and so we'll see what happens here is when you have ammonia in water, that's going to be an aqueous solution, and it forms NH4OH. This NH4OH breaks apart into the ions, where you have this ammonium ion, and then you also have the hydroxide ion. Okay, and so this is a forward arrow, small forward arrow, and then a big reverse arrow. So this reforms the ionic compound, which is the weak base. And that weak base is this ammonium hydroxide NH4. So you have all of those present in the solution. You have the ionic compound, and you also have the ions, the NH4 and the OH minus. Okay, so this is in comparison to the strong acid or strong base, you only have the ions. Ammonia is used in household cleaning solutions. It's the window cleaner, the blue Windex. And ammonia, being the example of a weak base, mostly still this complete ionic compound, where these ions are still bonded together. And it's the ion, it's the hydroxide ion, that is the dangerous part of the base that makes it slippery or taste bitter. And so the reason why you can use Windex or any weak base without using any gloves is because it's mostly this compound and not these ions. And the same is true about weak acids. The reason why we have vinegar in foods is because it's mostly the entire compound and not the dangerous part of the acid, which is the hydrogen ion.